Okay, good afternoon. So let me welcome everyone to today's academic training lecture. It's a great pleasure to have Julia Steinberger today with us. Julia has earned her PhD from MIT in physics, and then she has developed a line of research in the field of ecological economy. So her main focus is on the question to what extent or how to understand the relation between the resources a society uses and the performance of that society in terms of well-being and many other parameters. And one of the aims of that research is to develop alternative development pathways for how our society could transit to a carbon-neutral society. So I don't read out the bibliography or the CV of Julia in detail, but let me say that after research stays in Zurich, in Vienna, in Lausanne, she moved to Leeds, and then she was hired as a full professor at the University of Lausanne in the Department of Geography and Sustainability, I believe it's called. And that's where she is now. She is internationally renowned in her field, and in particular, she has been the lead author of one of the working groups of the International Panel for Climate Change 6 assessment report. Before I give the floor to Julia, let me make one more personal remark. So at CERN, we sometimes talk of the CERN family, and we mean many things by the CERN family. We mean the people who we are in contact with personally, scientifically, culturally. We also mean the people that share our values of scientific integrity and our values of being as researchers responsible for not only for our field but for society at large. Now, I got to know Julia only an hour ago over lunch, but it was just a pleasure to see with how many people at CERN you had strong bonds over many years. And it's really a pleasure to have you now here. So you know how to talk to physicists, obviously. And it's a real pleasure to have you here and to comment not only on your research field, but also on what we as physicists can contribute to stay within the planetary limits. Julia, the floor is yours. I should mention one last point I was asked. For those at CERN who are linked via the online tools, please consider coming to the main auditorium. That's the last request. Otherwise, Julia, the floor is yours. Thank you very much.
Thanks so much, Urs, and thanks for organizing. We are in a real room here, but the room with virtual people in it is bigger. There's a sort of 100 people, so we need to make sure to include them in the conversation. Thanks for the invitation. In the olden days, when I would come here, this auditorium would be full, and there was invariably several people who'd come up to me. You know, I wouldn't be giving the talk, but they would come up to me and say, I changed your diapers once, or whatever, you know, which is always a little bit weird. And so I am now toilet trained. So I just want to make that clear. Progress has been made, and it's just wonderful to be here. It's the first time I'm back at CERN since my father passed away, and so it's just a wonderful place. So thanks for the invitation. Okay, so I'm going to try to start by talking to physicists. I'll be telling you, okay, so one thing I should say, by the way, the IPCC report, so it's the Intergovernmental Panel on Climate Change, and that's just the first acronym you have to learn, then they continue. It's almost like physics. The report that I'm on is AR6WG3. The sixth assessment report, third working group report came out yesterday, and I spent the whole day doing interviews, and I did not have time to put any content in the slides just from the report itself. However, my research that I'm going to be showing you is all over the report, especially in Chapter 5, which is the cool one everybody wants to talk about. So consider yourself also informed of some of the latest research that came out yesterday. And I hope I'm a bit more coherent with you than I was in some of those interviews. So we're going to talk about the climate context a bit, just because you may or may not be consider yourself up to date on that. And I want to talk about my Living Well Within Limits project, and then we'll talk about what that might mean for physicists and research and action more generally. So a few words on the climate context. So every so often I have to change that slide. I mean, quite often. This is obviously a fairly recent disaster that happened rather close to here. One of my PhD students was from that area and spent some of his summer cleaning up, I believe. So we are now well advanced into the time when climate impacts are around us. So that's one of the points, is that when people try to stop action, they don't try to deny the science anymore. They move on to other arguments. That's why we should still not do anything about it. So in terms of scientific basis for the climate emergency, this is data from the report that came out in 2018, but things have changed in terms of we know a bit more now. But that report was a good one because it sort of lays out the levels of warming and the likely impacts. And the latest report on impacts came out on the 28th of February, and due to Russia's invasion of Ukraine, was pretty much not covered by the media whatsoever. Anyway, so we have a context, which is an international context, which is the Paris Agreement. And the Paris Agreement is not a scientific document, it is a government document. And as a result, it doesn't make a lot of sense. And one of the ways in which it doesn't make a lot of sense is it has two goals. So you want to keep warming below 2 degrees, but also as low as 1.5 degrees. So it's got two numbers in there. And then the governments, when they realized that they had signed up to a thing with two numbers in it, at some point realized, do we even know what that means? Do we know what the difference between 1.5 and 2 means? Doesn't sound like much, but come on, tell us. And maybe 2 degrees, maybe 1.5 degrees is too much, maybe 2 degrees is too much. So tell us some more information about this. And that's what this report tried to do, is basically answer the question, what have you signed up with, and what have you signed up to within this range of 1.5 to 2 degrees. And so there's a whole bunch of impacts that were covered in the report. This is just some of them. So I guess, okay, so first thing. When we're talking about warming and these degrees of warming, we have to be comparing it to a baseline, right? And so the baseline is considered the pre-industrial era. So it's always important to know where zero is. Zero is around, let's say, 1750, before the UK started burning a lot of coal. That's basically where 0 degrees is. So we're talking about warming relative to the pre-industrial era. And the second question is, where are we at in terms of warming? So do you know where we're at in terms of warming? Is that something that you've seen reported? We're going to make it a bit interactive. The people on the Zoom, you can also answer this question. What level of warming are we already at? Yes? 1? 1.2, 1.1 in the chat. All right, that's basically correct. So it's 1.1, 1.2 degrees. There are some error bars on it. So we're already very far advanced towards this 1.5 degrees. In fact, according to the latest IPCC reports that came out in August and February, we should be hitting 1.5 right around 2030 on our current trajectory. So we're really sort of zooming out on this in this trajectory. Anyway, so the main thing about climate change is that it's nonlinear. Things get nonlinearly worse with warming, and so that's sort of what this figure is trying to, what this table is trying to show. So so deadly heat waves at 1.5 degrees would hit 14% of the human population every 5 years, or 37%. At 2 degrees, that's 2.5 times worse. Arctic free from sea ice in summer, which it's not right now, would happen once every 100 years at 1.5 degrees, once every 10 years at 2 degrees. Insect species losing 50% of their range is 3 times worse. I mean, at 2 degrees, we're already a species that loses 50% of its geographic range is considered at risk of extinction. So that's like almost 1 out of 5 insects species, according to this study. And coral reefs die out completely at 2 degrees. They're gone. The impacts on biodiversity are really staggering. I think that this is something that we didn't realize up until recently. This is a study that came out in 2018. So I think that this has really not percolated into consciousness. Is in terms of so this was a study that was done on thousands of types of insects, plants, and so on, and sort of modeling their geographic range. And you can see that by the time we hit 3 degrees, we're talking about almost half of insects and plants being severely threatened in terms of losing half their range, being at risk of extinction. And 2 degrees is better, but it's still really high. And a quarter of vertebrates at 3 degrees. So which temperature are we currently heading for? Well, you might have realized that we're breaking all kinds of records. There was an all-time record in 2018, 2019, 2020. Obviously, there was COVID. Things went down a bit. But by 2021, they were heading back up, and indeed, they did surge. And so basically, including our current trajectory and the commitments that governments have committed under the Paris Agreement, because the government has signed the Paris Agreement, but they're actually doing the things they need to do in order to realize the Paris Agreement. So we're still heading for 3 degrees, possibly a bit more, possibly a bit less, depending on how you count. So we're heading for this future that is really devastating in terms of its impacts, and we're doing that in the space of decades, right, within the century. Now, I didn't know very much about this, and you might not know very much about it either, so I thought it would be interesting to at least sort of share this slide because it puts together so much data and it's so colorful. We all like colorful slides. It's mega complicated, but not by physics standards, obviously, but I'll just sort of walk you through it. So on the right-hand side, I'm not very good with right and left, so on the right-hand side, there's the future, the present and the future. So and you can see that the chunks are sort of 100 years apart. As we head to the left, we head into the past of the planet. And at first you can see that we're in tens of thousands of, or 5,000 years, and then 100,000 years, and then million-year intervals. So as you head that way, time compresses, right? Because you just don't have as much data, so you don't show it as much. And so you have the different, and you have the sort of different ages of the planet, and what you're seeing is the difference above pre-industrial temperature. So 0 is, again, on the vertical axis, pre-industrial temperature. And you can see a whole bunch of things that's kind of interesting. You can see that we've, the sort of past 12,000 years have been super important and super rare in terms of the geological record. They've been a stable, warm climate. And a stable, warm climate is when humans did everything. So we sort of crawled out of the last ice age. Ice ages are extremely unpleasant. The second to last ice age, humans almost went extinct, right? So ice age is not very nice. So we crawled out of the ice age, and then we started doing things like developing agriculture. And when we had agriculture, we started cities and writing and that stuff. That's why it says agriculture and civilization, because that's when we did that stuff, is 12,000 years of stable temperature. And then you can sort of see the ice ages. That's when it goes below 0. And it turns out that we appeared as a species, Homo sapiens, sort of in the middle of one of the ice ages. Not a very clever time, if you ask me. But we're only about 200,000 years old. And Homo genus is about 2 million years old. And what we're doing is that you can see that in the further past of the planet, you can see that temperatures were much hotter than they are now. So we have a comparison in terms of where we're heading. We're heating up the planet, and that means that we can compare future modeled states of the planet with past observed states of the planet. And that's what this study was doing. Burke et al., which I didn't write the reference. It's Burke et al. In PNAS from 2018. And what that means is we can compare models with the past, and that means that we're knowing how fast we're basically reversing trajectory. And so one of the things to understand here is that the rate of change of heating is unprecedented in the history of the planet. What we're doing now is unprecedented in terms of not the magnitude of the heating, but the rate of change. We're just doing it mega fast, really, really fast. So, and as we've seen before in the previous slide, species and ecosystems have no way to adapt to that rate of change. And what this means is that by the year 2030, on our current trajectory, we will have rolled back the climate clock to an age before humans existed, or before Homo genus existed, actually. If we reduce our emissions, we'll get there probably slower and stabilize there. on our current trajectories, we'll be heading 50 million years back by 2150. So this, I think it's just important to understand this, that the rate of change of what we're doing now is absolutely cataclysmic and unprecedented. And it's sort of hard to imagine how we cope with that. In fact, the latest report of the IPCC put forward the fact that there are limits to adaptation. At 1.5 degrees, we can probably mostly adapt, give or take. At 2 degrees, it becomes extremely challenging. Beyond that, we can't. So we've now left the Holocene. So this is just showing, sort of zooming in on the past few decades, and so that you can see that we're outside of this narrow band of Holocene temperature ranges, which is shown in pink. So we've already zoomed well out of that. And the question becomes, why? And who could possibly have known? Who among you has already seen this plot? 150 people in the chat, so in the Zoom. Who has seen this plot before? You have. Okay, a few people, and a few people have also, I guess, not seen it. So this plot is an amazing scientific achievement. That's the first thing to say about it, is that it's a prediction. It was actually done in around 1980, so it was published in 1982. And it shows on the left-hand side carbon dioxide rising in the atmosphere, so the result of fossil fuel combustion accumulating in the atmosphere. And that's on the left-hand side, and on the right-hand side it shows temperature going up as a result. So this plot was made by somebody who is absolutely fundamentally convinced, without a shadow of a doubt, and knew exactly the ratios between carbon dioxide accumulation in the atmosphere and temperature going up. And they predicted it really well. I mean, on our current trajectory, I mean, if you had a 40-year projection and you were as close as these people were in terms of carbon dioxide concentration in the atmosphere, you would be extremely proud of yourself. And they were off in temperature by a bit for various reasons. And this was a plot that was from an Exxon internal report. At the time, it wasn't even ExxonMobil yet. So one of the largest petrol companies in the world knew exactly what future they were creating for us. And I think that that's a really important thing to understand, is that the present that we are in and the future we are going into is a product of an economic system and of an industry. And so as we're not just talking about science here, we're talking about who knows what, who decides what. Right around the fun fact, we're learning more and more about when the fossil fuel industry first knew about climate change. It turns out that the earliest date that people have been able to trace so far was a speech by Edward Teller to the American Petroleum Institute in the 1950s. And nobody doubted him. Nobody said, oh, that's not real. What they did is petrochemical companies, they're very interested in the state of the planet and geology and all of these things. They started their own research programs. So they had in-house research programs on climate change, of which this is a product. Around this time, early 1980s, they shut down those research programs. They stopped them because they were convinced. They knew about sea level rise. They knew about all of that stuff. They were making their platforms higher than they would be otherwise because they anticipated sea level rise in the course of the next few decades. They shut down those research programs and turned off the millions for research and turned them into disinformation, denial, and delay. So that industry has been very, very careful not to prevent action. And that means that one of the things we have to realize when we're doing this research and we're trying to face this is that we have to take into consideration who our adversaries are. And I think that this is a helpful thing to try to think about. Okay, so this is sort of the long way around to motivate my research. So basically, this is Deborah Roberts saying the next few years are probably the most important in our history. This has only become more true. We have to absolutely peak emissions in the next 2-3 years and bring them down really fast if we want to have a chance of staying even within 2 degrees. So we're talking about immense urgency. And the implications for research is that if you want to do radical emissions reductions, getting to zero close within the next 20 years, the fastest and surest way to do that is to reduce consumption, is to reduce demand. So we're talking about a fossil fuel supply system, but instead of trying to substitute entirely for supply, you could just start not using the stuff. And the question is, how do you do that while protecting human populations? And so That's basically the research question that I tried to ask myself. How you can reduce consumption while preserving or enhancing well-being. And I'm not going to tell you the sad story of my life, but it was extraordinarily hard to get research funding for this. Basically, no research council would touch that topic for various reasons, and we can get into that if you want. But basically, finally, I did get the Leverhulme Trust to fund a really wonderful project, and so we came up with, so we call it Lily, Living Well Within Limits, and we came up with an analytic framework. So we needed a new analytic framework in order to do research, and basically this is very simple, but it comports a couple of things that we'll talk about. So you start, on your left-hand side with your planetary processes and resource use. On the right-hand side, you have social outcomes, so well-being, which is considered to be an outcome of need satisfaction. And in the middle, you have something called provisioning systems. And that's very important because the middle is not technology and it's not markets. It's actually an integrated perspective and social perspective. So it's provisioning systems are very much against mainstream economics. They're objects of study of heterodox economics. So we're talking about sort of a counterculture approach to understanding social systems and the economy as integrated social and technical, social and physical systems. Okay, so of course, as you heard, I have a physics background, so this is all very esoteric, right? Especially probably the well-being part. And it kind of sounds almost like an insane thing to do to study well-being. So the question is, how do you do it? And so we had to go and do some reading. And it turns out that it's very undignified when you do this research because you have to start reading stuff that goes back very far in time. And it turns out that you pick fights, you become part of arguments that involve people who've been dead for a couple of thousand years, which is extremely undignified. So welcome to, this is the cartoon version, right? But I figured that's probably good for you guys. It's good for me. So welcome to ancient Greece. Because some of the people who were thinking about what is the meaning of human life, what does it mean to have a good life, were doing a lot of very high caliber thinking and writing around that time. And one of the first people to sort of articulate his perspective very clearly was Aristotle. Obviously, he had a lot of other contributions to science. But his perspective is a very social perspective, and it's about realizing human potential. So well-being means to be able to live life as fully as possible and flourish within one's society. Which might sound perfectly sensible, but it's not the meaning that we usually use today. And the reason for that is just a couple of decades later, Epicure came on the scene, and he had a very different perspective. So for him, he sort of had a force field perspective, which is sort of more the way people like to think in terms of the physics and actually economics as well, which is well-being means achieving the most possible positive and least negative feelings possible. So it's sort of a very personal perspective, it's a very emotional perspective, it's about feelings, and it's about maximizing your integral over feelings, right? You want most positive and least negative. And that perspective is very, very different. And like all good academic disputes for your career, it's very important to keep them going as long as you possibly can. And so, indeed, the two camps persist to this day. And so you have to choose a team. If you're going to study well-being or think about it, you have to choose a team. You don't have any choice. So if you're Team Epicure, what does this mean for you? You might view well-being, you might interpret it as an emotional perspective, as an emotional state, like happiness. It's a very individual perspective, so is the individual happy, is the question. You might measure it through a happiness indicator. So this is something that's established in research now. You can go around and ask people how happy do you feel on a scale from 1 to 10. It turns out it matters if you ask from 1 to 10 and 10 to 1, you get different results. Be careful. And you have international, you have the UN has a global happiness report and so on. So if you're thinking about it from an economic perspective, you have this thing called a utility. You see Homo economicus, the human agent in the economy, is represented as a utility maximizer. So basically, your economic agent is a person who's going around the world with a budget, and that budget, they spend that budget in the market, and that's how they maximize utility, is through their expenditure choices and volumes. And that means that from that perspective, from this sort of Epicure perspective, or descendants of Epicure, economic growth is viewed very positively because it's sort of an indicator of mega welfare. It's a macro indicator of welfare. More economic growth means more income, means more consumption, means more positive feelings. Boom. So that's one perspective. If you're Team Aristotle, oh, and by the way, Team Epicure is dominant in our culture and in our economics, and also in our politics. So that we live in a world that is dominated by that perspective on well-being. However, if you want to be Team Aristotle, you have a very different perspective. So it's not about happiness. It's not about emotions. I will not care if anybody's happy or not. That's a horrible thing to say. But it's about flourishing. It's, do you have a chance of realizing life plans? So do you have the opportunity, is your society giving you the opportunity to make plans about your life that you can then realize or not? So nobody promises you a rose garden, but they promise you human potential, that you can realize it. It's a social rather than individual perspective, because in this case, well-being is a social product. You are either in a society that allows you to do this and provides the conditions, or not, where you're deprived. In terms of measuring it, it's often measured through multidimensional indicators or indices that have multiple dimensions in them, like Human Development Index or the UN's Sustainable Development Goals. And the idea of the economy is that the purpose of the economy is to support human potential. So the view of development is to support human potential, regardless of whether growth is happening or not. And within the Living Well Within Limits project, we decided very early on that we were part of Team Aristotle, and then we wrote a couple of papers explaining why and what that means for energy and climate. And you will find our papers all over the new IPCC report. It was quite extraordinary. People listened to us. Okay, now, that's all very fun, but if you're physicists, you probably like to test things. So can we test Aristotle's theory? And so the way we translated Aristotle's theory is that you have well-being when your needs are satisfied. It's a negative perspective on well-being. Your needs are satisfied up until a certain level, then you can make your life plans. And the way we're doing this is we're basically, this combination of universal need satisfiers with well-being outcomes is something that we based on the theory of human need of Doyle and Guff. Ian Guff became a good friend. It's a really interesting book. I recommend it. So we're using Doyle and Guff's framework. And then we decided to test it. So what we're looking for here is empirical evidence that multidimensional need satisfaction is a precondition for well-being. So need satisfaction means it's multidimensional. You have several of them that are non-substitutable. You cannot substitute food for education or vice versa. And once they're satisfied, you don't need more than that in order to do your flourishing, realize your life plans. So that's the hypothesis that we're trying to test. So what we did is we assembled an international database of needs satisfaction, and average life satisfaction is actually sort of more of a happiness, sort of subjective well-being indicator. And if a country had all the countries that had zero needs satisfied, we put them in the zero bucket and we averaged their life satisfaction. All the countries that had one need satisfied, we put them in the one bucket and we averaged their life satisfaction, and so on. And that was the result. And we were honestly completely flabbergasted because we had not expected anything that strong. But that gives us pretty good evidence for the fact that well-being is at least very strongly associated with multidimensional need satisfaction. And if you look at physical well-being, sort of physical health, so average healthy life expectancy in years, you get an even stronger relationship. So it turns out that one actually exhibits saturation with need satisfaction. So at some point, you sort of max out. Anyway, so we thought that was pretty good evidence to start with. Then we decided to test Kate Raworth's donut. And I probably just said stuff that makes no sense to you. How many of you have seen Kate Raworth's donut economics? You'd also seen the plot from Exxon. So anyway, so the idea of Kate Raworth is that, so her book is extremely readable. She's fun, intelligent, and writes well, which makes her sort of an outcast in academic economic circles, as you can imagine. But she basically is trying to get us to think about a new way of doing economics, where we try to stay within planetary boundaries and satisfy human needs. So this idea of a double challenge. You have the environmental ceiling and the social foundation, and you're trying to stay. You don't want to be socially deficient, and you don't want to be beyond planetary boundaries. So we decided to test it. Again, we had lots of data. I'm not going to bore you with that. And we found this kind of framework. So basically, you can see a country like Germany. Switzerland is similar, slightly worse, I believe, but didn't have as much social data. So you have a country like Germany, which is transgressing multiple planetary boundaries. That's all the red stuff, and but satisfying most of the social indicators. There's a lot of blue there. There's not a lot of red in that part. Whereas, for instance, a country like Sri Lanka is not transgressing any planetary boundaries, but is also having deficiency on a lot of the social indicators. And when we look at the international data, that's basically what we see. This makes sense. You can see that so here what you have is the number of biophysical boundaries transgressed on the horizontal axis. Every time a country transgresses another one, we jump it horizontally by a notch. And social thresholds achieved, so these are need satisfiers achieved. So every time a country satisfies another need, we bump it up a notch on the vertical axis, and that's how we place the countries in this plot. And what you can see is that Sri Lanka and Germany are not unrepresentative, right? So you can see that there's a whole bunch of countries that don't do so well on social thresholds and also don't do so well, but don't transgress planetary boundaries. There's a whole bunch of countries that do great on the social thresholds, but are terrible on planetary boundaries. And because we live in the times we do, there's a whole bunch of countries that are the worst of both worlds, that do terrible on social thresholds and terrible on planetary boundaries, like, for instance, South Africa, China, and so on. Oh, and by the way, I should mention, these are all trade-corrected indicators, right? I should have mentioned that. They're all trade-corrected indicators. So, yeah, and the one neighborhood that is conspicuously empty is the one we really need to get to, not to be in danger and not to be living terrible, deprived lives. And when we showed this to Kate Rayworth, she was a bit depressed, but one of her conclusions was, we are all developing countries now, because everybody has to move. Everybody has to think about a new way to run our economies and to provide the good things for our societies that we need to do. And so the research questions becomes, okay, we can't learn from exemplary countries. The question is, how can we go from here to there? And that's what I want to talk about in terms of the research we did subsequently. So one of the things we looked at was we decided to look within countries, because when we're looking at country averages, they hide a lot of inequality. So we're pretty sure that macro social factors, including distribution, are extremely important. And we now have the toolkits, the databases, and the methods where we can do a lot of work on inequality and understand a lot more about it than we did before. And so this is what my PhD student Yannick Oswald did. The paper says what it did: large inequality in international and intranational energy footprints. So footprint means it's corrected for trade, between income groups and across consumption categories. So that gives you like lots of dimensions. We're looking at different countries, within countries, income groups, and consumption categories. And of course, the BBC decided to cover it. I was happy. In their own way, they were like, climate change, the rich are to blame. And this is true. They were not wrong. Okay, so we're measuring direct and indirect energy footprints. We can talk about the method if you want. The method's kind of cool. It's called Environmentally Extended Multi-Regional Input-Output, or EEMRIO for short, another acronym. We look at expenditures of households, so we have categories of products based on the detailed expenditures of households within those countries. We're looking at 86 countries in the EU and World Bank, and each of these countries has income classes. And I'm not going to talk, so the most interesting finding, I would say, had to do with inequality of product use. So these curves are called Lorenz curves. They're very used in inequality economics. The way you construct a Lorenz curve is you start at 0, 0. 0% of the population has 0% of the resource use. and you have to end at 100%, 100%, 100% of the population is responsible for 100% of the resource use. And in the between, you rank them by relative wealth, and you sort of go up that curve. And so when you see statistics saying that, the bottom 90% of the world are only responsible for 10% of a certain type of consumption, that's what they're doing. They're reading off a Lorenz curve to get that information. And it's also how you calculate Gini coefficients. Anyway, so what you can see here is the energy footprint is the red one. So and the other thing is the line of perfect equality. If everybody in the world had exactly the same consumption, we would lie along that line of perfect equality, which is the diagonal line. The further away you are from the diagonal line, the more unequal you are. So the further down and to the right. And so what you can see is that energy itself, energy footprints themselves are already quite unequally distributed, but some are more equal than others. And the more equal ones have to do with food and residential fuels, heat and electricity. The more unequal ones have to do with transportation categories, including package holiday is sort of a weird category that has a lot of flights in it. And so one of the things that study allowed us to do is it allowed us to map product categories. And so using the kind of data in the previous slide, but within each country, this is not international, this is really like all countries in the world sort of using probability density curves. Anyway, I shouldn't have said it's too complicated. But basically, we map product categories by sort of a quadrant analysis. So along the horizontal axis, if something is on the left, it means that it has less energy intensity, less energy per dollar spent in the economy. On the right-hand side, more energy per dollar spent. So we'll obviously be interested in the more energy-intensive products. And on the vertical axis, on the lower side, these are things that are consumed disproportionately by poor people. Now, rich people consume more of everything at this level. But this is a proportion of the budget. And on the top, it's consumed disproportionately more by rich people. It's a larger fraction of their budget. And so we did this. We got all the data and we plunked it on this chart. And we were honestly, again, really surprised to see what's in this, the rich people in high intensity, the luxury and high intensity quadrant is almost entirely, well, pretty much entirely populated by transport categories. So one of the things that really shows up here is that transport is how rich households worldwide spend their excess income. It's on flights, it's on cars, it's on big cars that are bigger cars driven for longer is a large part of it. And this is really a pattern that we see around the world. Whereas the high intensity and the basic but high intensity is heat and electricity, that's energy use in the house. So it's dwellings, it's buildings. So you see this real dichotomy show up between buildings and transport. And so that's a really interesting point because here we're faced with a problem that we cannot grow out of. If rich people are, there was a sort of this dream at some point in terms of ecological development that rich people would spend their money on operas and paintings. They spend their money on SUVs and travel. So we need to do something in order to change that. And so this is a problem you cannot grow your way out of. You have to tax and regulate in order to get that to change. Whereas obviously if poorer people are spending a disproportionate amount of their income on heat and electricity, it's not because they want to. It's because they have to live a decent life. So that means that the households that are spending money on heat and electricity in the home, what they want to, we have to provide the framework conditions for them to be able to do that with lower energy and lower carbon. They will not have the money to do that themselves, otherwise they would have already done it. So we need public investment in efficiency, retrofit, and low carbon energy generation. And if you were clever, you might connect your taxes in one to investment in the other. I just really want to drive home this point that transportation is awful. So this is a study that came from the IEA in 2019, and it basically shows the change in CO2 emissions by energy sector in the last decade. And this is just change in energy. It's like what went up, what went down. And you can see that the first one is power. So that's electricity worldwide. That's coal-fired power plants. You might have guessed that. The second one is just cars that are stupidly bigger than they have to be. It's just, these cars do not serve a purpose besides making money for the car industry. They are not more useful than a smaller car. So this business of SUVs being the second driver sector-wide of emissions for the past decade is really something. So it's really causing macro problems, and all other cars actually went down in terms of emissions. So it's really extraordinary thing. Because cars are getting more and more efficient, they're technologically extremely performant, but all of that is out the window because of SUVs just being big. And Switzerland, fun fact, has the worst carbon dioxide per kilometer of its vehicle fleet in entire Europe. Okay, so this is Tim Gorsing from Oxfam saying exactly what I said before. So I will move along, but basically we need to tax stuff and invest. This is another result from a couple of years ago, the emissions gap report, which again shows this is for CO2 emissions, and the inequality is actually starker than I showed in the previous energy result. So let's just focus on the circle one. You can see it pretty well. Top 1% of income earners is 15% of global emissions. Top 10%, which includes the top 1%, is almost half of global emissions. The bottom 50%, the poorest people, are 7% of emissions, which, if you were keeping track, is less than half of the top 1%. So we're really talking about a global system that is massively unequal. And so one of the points is that, obviously, if we reduce that inequality and we cut down on overconsumption of the top 10%, which might include a lot of people in this room, but still, you could still live comfortable lives if you were at in the 89th percentile or whatever, that would be half of the emissions in the world every year that we'd have gotten rid of. That's quite something. We were sort of increasingly upset about the fact that this was not enough of a topic in research. So we wrote this paper, which we decided to title in a very subtle way, Scientists Warning on Affluence, which I think is interesting. You might want to have a look at it. It was one of the most cited papers in 2020. We basically just talked about the evidence, and we also talked about strategies for dealing with it. And my students were really happy because we got eco-anarchism in nature, which was as strategies for dealing with stuff. And my students who are eco-anarchists were very happy. So that's that. Anyway, just in terms of ways of thinking about how we deal with this, might be interesting to think about. Okay, so in terms of more quantitative modeling, we decided to look at what happens if we make distributions more equal. What are the consequences there? And so we made a model basically it's a ceteris paribus model. We take the state of the world as it is now, and the only thing we do is we slosh the money around. And then we see how the energy distribution changes, how you basically change energy footprints. And so what happened is, this is where we squeeze income back and forth. So this is basically, this is what our distribution is doing. It's a log normal distribution. And the main result here is that as that distribution changes, so what I should say is the sigma, basically the blue curve is very equal. It has a low sigma. And the green, sort of outer green curve is the most unequal. And in terms of Gini coefficients, smaller is more unequal, and smaller is more equal, larger is more unequal. So if you look at the top plot, what's changing in terms of the global energy consumption is not much. So as you make the world more equal, like really equal, energy consumption globally would go up by about 7%, which is not very much. If you make the world super unequal, you have only oligarchs left and nobody else has any money, energy use goes down by 3%. So honestly, that's not very much change. Basically, the quantity of money is what matters, not how it's distributed in terms of global energy use. But what really changes in this model is the sector in which energy is used. So you can see that sector shown as we change the Gini coefficient on the top axis. And what you can see is that a more equal world uses more orange stuff, which happens to be heat and electricity in homes. And a more unequal world uses more pink stuff, which is transport. And so that's a really interesting result because it basically tells us, effectively, that a more equal world would be easier to decarbonize. So when we saw that result, Yannick Oswald then wrote a paper in The Conversation basically explaining that basic point, because dwellings and buildings are easier to decarbonize than the transport sector. So all things being equal, a more equal world would be easier to decarbonize. So that's already one direction in terms of understanding the world better, is distribution, who consumes what type of, and what do people consume energy for. Now, we did another study where we decided to look at this intermediate stage. So we're looking at energy, as usual, need satisfiers, as usual. And then, and this is an equation which you'll actually understand. You'll be the first audience I've presented it to that will understand the equation. It's wonderful. It's very basic. But then we decided to look at factors of provisioning systems. We decided to look at this thing in the middle and see how turning some dials in the middle would change the system. And so we have a second term in the equation, and then we have an interaction term that allows us mainly to determine the domain of validity of the result. Like where in this parameter space is the result actually meaningful. And so this is basically showing the same thing. We're looking at energy use versus need satisfiers. Look at the bottom part, the thing that's called B. It basically says what variables we're looking at. But the bottom part of the plot. So basically, need satisfaction, energy use, there's this sort of saturation relationship. At low levels of energy use, a little goes a long way. At high levels, it sort of flattens out. Okay, that's sort of what your curve generally looks like. If you have a high value of a beneficial provisioning factor, this stuff in the middle, you're basically moving the curve up. And you're making it easier to achieve need satisfaction at lower energy use. If you have a detrimental, you're pulling a factor, you're pulling the curve down. You're making it harder to achieve need satisfaction at any level of energy use. And so we did this study, crunched the numbers internationally, blah, blah, blah. And if you remember green, good, red, bad, that's all you need to remember for the slides. So the positive, so this was, it was so interesting because if an effect was positive, it was generally positive across all the relationships, and if it was negative, the same. So what counts is if you have a bunch of green bars, that means that factor is beneficial. And so the beneficial factors are things like public service quality, public health coverage, trade and transport infrastructure, electricity access is mega positive, access to clean fuels, same. Urban population is kind of positive. Income equality, very positive. Democratic quality, very positive. There were two factors that didn't really matter. Trade penetration and foreign direct investments, they don't really matter. And there were two factors that were negative. And interestingly enough, extractivism we kind of expected, to be honest. Extractivism is your economy dependent on extractive activities for its GDP. Basically. So if your economy is really dependent on mining and fossil fuel extraction and that kind of thing. So extractivism, this is a known result in economics from decades and decades and decades. It sometimes goes as the resource curse or as Dutch disease. Basically, if you have an extractive sector dominating your economy, it basically cannibalizes that economy and makes it a bad society to live in. And so this is something we're observing here too. Extractivism, not good. The other one is maybe more surprising, economic growth. So economic growth above a moderate income in this case is a negative factor. It makes it harder to achieve need satisfaction at a certain level of energy use. So that was interesting. And this paper is well represented in the latest IPCC report. Then we decided to do modeling. So can we model a different future? So here we're using a framework developed by Narasimha Rao of Yale. What we're doing is we're connecting these needs again to sufficient level of energy services. I'll show you what that looks like in a minute. And then we use available technology. So we're improving technology, but we're not making up technology. So like all the models that produce tons of negative emissions. That's made up technology. We're using only demonstrated real technologies. We have equal distribution. Everybody has the same access to needs satisfiers, to energy services, and we result in lower demand levels. So what sufficient energy looks like for each person, you might disagree, but we tried to basically provide some kind of basis, considering how many billions of people live in real material poverty. This is way beyond that. So we have nutrition, we have living space. So the living space is not huge, 15 meters squared per person, but it is heated or cooled year-round to 20 degrees. So it is extremely comfortable living space. So we're not talking about unheated or uncooled living space. And that's dependent on climate. So every country in the world we looked at what climate would imply for heating and cooling. We have water, communication. Everybody has mobile phones. There's one laptop per household. Maybe we should have more, but it doesn't matter. That stuff doesn't matter. Everybody has Wi-Fi. Everybody has data. There's health. So we have hospitals, education, and so on. And we included the embodied energy in all the infrastructure for everything. And we know we can do this in a reliable way because we have these input-output models that allow us to do this. And that's another sort of depiction of what the model does. So we basically have various kinds of decent living standards that are connected to different types of consumption, and we sort of go up the infrastructure chain. And our results show a real change compared to what other models previously came up with. So we have global final energy is, in exigils, there you have historic trends, so we're around like 400 something now. The IEA reference scenario, the IEA is the International Energy Agency. Their reference scenario is like business as usual, you keep going. 2 degree scenario, you sort of flatten. And below 2 degrees, you kind of even decrease a bit, but you never really get very low. There was a previous low energy demand scenario from Arnulf Grubler and colleagues, around 250 exajoules, and our scenario lands you around 150. So basically, in theory, decent living for all, decent living energy for all would be achievable at 40% of current energy use despite population growth. So that result sort of shook people up because nobody had ever even tried to do it. I mean, it's not like it was hard to do. It's that nobody had ever cared to try to estimate it before. But in theory, it's possible for everybody to live good lives at a really, really much lower level of energy use. So I'm going to wrap things up. I'm not going to tell you about the political economy stuff. I think that's a bridge too far. So we'll skip that. It's all words, no graphs. So we'll go on to sort of some ideas of what more physicists can do. I promised I would try to talk about that a bit. So looking for a few more good physicists. There are a lot of physicists already active in these domains. In industrial ecology, which is where I came from, like it was basically founded by physicists, so we have our great old men as well, like Bob Ayres. But the reason that physicists are useful in this kind of work is a lot of good things. So ability to consider systems, an eye for system constants and key parameters. You don't care about third or 15th order relationships. You keep your eyes on the prize. There's also generally physicists have a desire to identify their own version of what the big question is and don't respect economists a lot. That's very important in this kind of domain because otherwise economists rule. They really do rule our world. So it's very important to have people around who don't care what they say. There's a healthy disregard for academic disciplines and you don't necessarily care about methods. And you might differentiate between meaningful versus pointless results. That's also good. And good quantitative modeling skills are always nice to have. And also by applying multiple methods. A lot of research domains are not very robust, and people don't care about applying multiple methods. They're like, I applied one method and found this result, and you applied another and found another one, and we're just going to disagree now. And anyway, that's not very satisfying. I think the other point why physics would be important is because we really have a problem with ideology, and physics has a history of going up against ideology. So we are right now in a culture and a belief system and societies that have a hegemon, and and that hegemon is growth, the idea that growth is progress and that the purpose of our societies is growth. And it's I really compare it to, to seeing the Earth as the center of the universe, right? And the idea that something else could be the center of the universe is considered heresy. So the goal of economic growth is really the secular religion of our societies, and we need people who are willing to challenge that. Because basically all social goods are automatically ascribed to growth. Countries compare their position based on growth. That's what the G and G7, they're comparing their growth rates, the level of their economies. The goal of growth is is ideological than empirical. So one of the points here is that growth is often justified because it's supposed to alleviate poverty, but we know empirically that it accrues to the wealthiest. It is not distributed. Growth itself leads to rising inequality, according to Piketty. Growth can only account for fractions of the improvement in life expectancy, for instance, over time, which is a older result that I re-demonstrated in 2020. And growth cannot be decoupled from resource use. So we have problems with growth, and it would be nice. I think physicists would be less generally inclined to follow what economists say with a blind perspective. There are a few nice research missions for physicists, doing empirical research on how we could do things differently, such as the kind of modeling I showed you. It's really not so hard. You can create novel economic models that explore what growth-proof societies look like. There was a really nice example from D'Alessandro in 2020 from Pisa. And you can also become engaged because it turns out that saving the planet is not a spectator sport. And it is not by coming to this talk that it's going to happen. It's really not. And I think that there's also a lot of inspiration for physics. Physics has a history of political engagement for things like people like Joseph Rotblat and the establishment of pugwash and efforts around nuclear disarmament in a way that other academic communities are a lot more reserved and shy in terms of imposing themselves in terms of public discourse. So I think that would also be a welcome addition. I always end my talks with this, so from understanding to action. We are in really bad times. I hope that came across. So we do not no longer have the luxury of thinking about gradual transitions. In fact, the IPCC, we don't even talk about transitions anymore. We talk about transformations. Transitions were possible 30 years ago. Now we're really in crisis mode, and we have to act extremely fast. So we're talking about radical transformation. I would argue that the popular movements like the student strikes, the Sunrise Movement, Extinction Rebellion, I'm actually going to an Extinction Rebellion thing tomorrow. I'll realize this. And one of the things that I wonder is our research supporting them? So are we as an academic community supporting the people who are trying to change things? How can we contribute and participate? So in my view, I really follow what Charlie Gardner and Claire Worley wrote a couple of years ago in Nature, Ecology, and Evolution. They had an article called Scientists Must Act on Our Own Warnings to Humanity. And the basic point is the scientists who alerted the world to climate and ecological crises have a moral duty to join the popular movements. You can't just talk about it. You can't just be aware it's happening and sit back. I'd really like to get that point across to you. You cannot be aware of this and sit back. That time has gone. We are not in a technocratic change model. It is not because of awareness of the problem that things are going to change. You have to step up. I'm part of the scientists who endorse mass civil disobedience. We even wrote a paper called From Publications to Public Actions. Get it? It's hilarious. It's a play on words. And trying to change the role of universities. So universities and academic institutions should be the social brain that allows us to make this transformation, but are we doing it? So that we try to think through how we as academics who are paid to help society think through problems can actually help with these kinds of issues. And the other point here is that it was all very fun in the early days of the climate strikes and Extinction Rebellion and seeing my students go out on the streets and going out with them, but they're being criminalized. I'm being criminalized. I've got an ongoing court case because I walked into a UBS on the wrong day. But for instance, in the UK, they're passing new laws saying that if you block a road, you get a 15-year jail sentence. And this is happening around the world. It's happening in Switzerland too. There are 200 youth climate strikers and Extinction Rebellion and other people who are in the courts just in Geneva and Vaud. So, and they're going after people with really extreme measures. So one of the things we wrote in this letter was, it has become abundantly clear that governments do not act on climate without pressure from civil society, so threatening and silencing activists seems to be a new form of anti-democratic refusal to act on climate. So I think one of the things we have to understand is this is a struggle. It's a struggle involving power. And you got to choose a side, and you got to think through how you use your brain, how you use your hours in your day in order to help. So that's my challenge to you. Thank you.
Okay. Thank you very much, Julia, for this talk, for this thought-provoking talk. I propose the following. We take now questions. At some stage, we will switch off the recording, then further questions can be asked. I will let you know, but for the time, the questions that are asked are still kept in the recording. I start with questions.